Lesson 10 is key features of logarithmic functions, and in 10.1 we're going to be identifying key features from a graph. So example 1, state the following key features of the log graph. So starting at the top with vertical asymptote. So all log functions have a vertical asymptote on their graph. Remember that asymptotes are just like boundary lines that the function will approach but never cross. So we have the vertical asymptote drawn on this graph. It's that red dotted line. And to write the equation of a vertical asymptote, all vertical lines are x equals, and it's going to be x equals wherever the line crosses the x-axis, which is at 1 in this case. So it'd be x equals 1. If your asymptote was not drawn on the graph for you, it would be the vertical line that the function starts to like approach and kind of like cuts off the function, I guess. So like how on the left side of this function it starts going upward around that line x equals 1. And then for domain, since log functions have a vertical asymptote, their domain is going to be restricted because you can see that my graph is stuck on the right side of that vertical asymptote. It won't go to the left side, so that means that the domain can't be all real numbers. So if we're stuck on the right side of the asymptote, we could write the domain as x is greater than 1. So that's just saying like everywhere to the right of x equals 1 of that asymptote, or you could write it in interval notation, and interval notation you say like kind of the leftmost boundary and then to the rightmost boundary. So since we're starting at 1 and then we're going everywhere to the right, it'd be 1 to infinity. And then remember with interval notation, use brackets or parentheses to indicate if the value is included in the domain. So since we have a vertical asymptote at 1, you won't actually ever cross that line. So we put parentheses around 1, and then it's always parentheses around infinity. And then for range is how far is the graph extending up or down. So you can see the graph goes like up forever right here and down forever on the right side. So it's covering all of the possible y values. So our range would be all real numbers for all log functions, or if you were to write that in interval notation, it would be from negative infinity to positive infinity. And then for the end behavior, it's how are like each of the tail ends of the graph finishing. So if we look at like the left side of our graph right here, normally we say for end behavior, like as x approaches negative infinity, that would be like the left side, but the graph isn't going all the way to negative infinity for the x's because of that vertical asymptote. It's getting cut off there, which that vertical asymptote was at 1. So that means that x is approaching 1. So that's describing this part of the graph. As x approaches 1, what is it doing? It's going upward. So f of x would be approaching infinity since it's going up. And then the second line of end behavior, so as x approaches, and this is supposed to describe the right side of the graph, so the right side of the graph does go to the right forever. It doesn't have a boundary line, so that one would be as x approaches infinity. F of x approaches, this is asking if it goes up or down. Since it's going like down as it's going to the right, you would say f of x approaches negative infinity. And sometimes it looks like with log functions that there's like another asymptote, say down here, because the curve starts to flatten out, but they'll only ever have a vertical asymptote. And then for increasing or decreasing, you're looking at like the trend of the graph. Think of it kind of like in terms of slope. If it's going up and to the right, it would be increasing. Down and to the right would be decreasing. So our graph is going down and to the right, so this would be decreasing. For the x-intercept, that's where does it cross the x-axis? It crosses at 2. So it'd be the x-intercept would be the point 2, 0. And then for the last two parts, positive or negative, that's asking for like where are the like x values, or sorry, excuse me, where are the y values of the function above or below the x-axis. So kind of like where is the function giving you a positive output value or a negative output value. And you look at that by determining like the y values, whether they're positive or negative. And on a graph that looks like above and below the x-axis. So that purple section, that would be the positive section since all the y values are positive. That blue section, that would be the negative section since all of the y values are negative. So since they like change from positive to negative at that x-intercept, that's going to be our boundary line, so at x equals 2. So for where it's positive like all along that like kind of purple section, which a lot of times we would write it as like just x is less than 2 because it's to the left of that x equals 2. But it's not like everywhere. It's not all over here because there's that boundary line. So we really have to say when x is between 1 and 2. So when x is less than 2 and greater than 1 is where it's positive. Technically, it would be like undefined over here. So we wouldn't be able to say it was positive. We'd say it's undefined. And then for where it's negative, so it starts becoming negative like after x equals 2. So we would say when x is greater than 2 is where it would be negative. Okay, so positive is asking for what intervals is it above the x-axis. Negative is asking for what interval is it below the x-axis. Okay, so moving down to example 2, state if the function is increasing or decreasing and find the x-intercept and the intersection point of h of x and y equals 1. So a bunch of kind of different things to find here, but for whether it's increasing or decreasing, we're looking at if the function is trending like up and to the right or down and to the right. So you can see like this graph is finishing up and to the right, kind of like a positive slope, so that would be increasing. And then for the x-intercept, you can see it's crossing the x-axis right here at x equals 1 or 1, 0. And then for the intersection point of h of x and y equals 1, you can see that the function is in blue, and then the y equals 1 line is that orange dotted line. So the intersection point between the function and y equals 1 is right there at the point 2, 1. And I know that kind of feels like a little bit random to find that, but the reason that that point matters is because if you have a simple log with no translations or anything like that in it, that intersection point is going to tell you what the base of the log is. So I could technically write the rule at this point. It'd be h of x equals log, and then I'm looking for like the x coordinate from the intersection point, so 2. So the base of the log would be 2, and then be log base 2 of x. So h of x equals log base 2 of x would represent this graph. We're going to talk about that more in the next section though. Okay, so the next section is going to kind of combine 10.2 and 10.3. 10.2 is writing like the key features from rules, and then 10.3 is going to be taking it all together and just going ahead and graphing it. So for vertical asymptotes from rules, all logarithms in the form f of x equals log base b of x plus k have a vertical asymptote at x equals 0. So that means kind of like these would be parent function logs, and if there's a plus k, there could be a vertical transformation. But if we picture like, you don't need to draw this or anything, if I picture like the parent function with a vertical asymptote at x equals 0, if I like have a vertical translation, it's going to move the graph up and down, but it's not going to move it left or right. Moving it left or right is what would move that asymptote. So as long as you don't have any like horizontal translations like h, the asymptote would stay the same. So these are a couple of examples of functions that have just vertical asymptotes at x equals 0. So let's say you have f of x equals log base 2 of x. That asymptote is at x equals 0 because it's in that form of log base b of x plus k. The thing that would change it so that like it would no longer technically be in that form is if you had like say log base b of like x minus h or something in parentheses. It would have to be something added or subtracted inside the parentheses because that's what would like shift the graph left or right and then shift the asymptote. So another example is if you have g of x equals log base 1/3 of x plus 1. Again, that plus 1 is added, but it's not in parentheses, so it's not a horizontal translation. So it wouldn't move the asymptote, so the asymptote would stay at x equals 0. Okay, for finding the x-intercepts, to find an x-intercept, set the function equal to 0 and solve for x. So that means that we are like taking 0 and we're putting it in for f of x. So like completely replacing f of x with 0, not finding like f of 0, because like f of x is y, and if I have an x-intercept, or sorry, yeah, if I have an x-intercept, I thought I said it backwards. But if I have an x-intercept, that's going to be the point x0 is what makes it on the x-axis. And so the y-coordinate is 0, so we would replace all of f of x with 0. Okay, so instead of f of x equals, it would be 0 equals log base 5 of x. And there's a couple different ways that we can do this. We can like exponentiate to cancel it out. We can just rewrite it from log form to exponential form to solve for x. I'm going to rewrite it for a and cancel it out for b. So if I were to rewrite it, the base of the log becomes the base of the exponential. So it'd be 5. And then I know that like when it's in log form, logs isolate the exponent part from the exponential. So it'd be 5 to the 0 and then equals x. And anything to the 0 power, so 5 to the 0 would be 1 equals x. So my x-intercept would be at x equals 1 or at 1, 0. And then for b, same start, I would put 0 in for f of x equals log base 2 of x plus 3 minus 5. For this one, I'm not going to rewrite it. I'm going to cancel out the logarithm by exponentiating. So before I do that, I want to get the log by itself. So I'd have to cancel out that minus 5 by adding 5 to both sides. So 0 plus 5 would be 5 equals log base 2 of x plus 3. And then if I want to cancel out the log, I have to exponentiate both sides by the same base. So the base of the log is 2. So I would have to exponentiate by 2. So it'd be like 2 to the 5th. And then equals 2 raised to the log base 2 of x plus 3. And then 2 to the 5th is like 5 2's being multiplied together, so it's 32. And log base 2 raised to the log base 2, these all just kind of like wipe each other out. And it would leave us with just what we're taking the log of, so just x plus 3. And then if I just want to get x completely by itself, I'd have to subtract that 3 over. So it would be 32 minus 3, so 29 equals x. So the x-intercept would be 29, 0. So moving down to end behavior, to find end behavior from a rule, you need to determine if the function is increasing or decreasing and find the vertical asymptote. So we're going to use the rule f of x equals log base 5 of x. To determine if it's increasing or decreasing, we have to look at the base of the log. If the base is greater than 1, it would be increasing. If the base is between 0 and 1, so less than 1 but greater than 0, it would be decreasing. So this one, our base is 5. 5 is greater than 1, so it would be increasing. And then for the vertical asymptote, this goes back to, I'm going to zoom out so we can see it up here. Anything that's in the form of log base b of x plus k, basically if you don't have like a number that is being added or subtracted from the log in parentheses with the x, your vertical asymptote is going to be x equals 0 because there's no horizontal translation that moves it side to side. So x equals 0 and it's increasing. So I'm just going to draw like a little kind of like sketch, and this could look really not that much like what our actual log looks like, but can still help us figure out the end behavior. So we know that there's a vertical asymptote at x equals 0. And then we know that the log is increasing. So if it's increasing, it's going up and to the right. And that little sketch is really all you need to be able to like state end behavior. So for end behavior, we'll do the left side of the graph. So as x approaches, and on the left side of the graph, x is approaching the asymptote. So this one would be as x approaches 0, because that's what the asymptote is. F of x approaches, and that's asking if it goes up or down. So as it approaches the asymptote on the left, it goes down. So f of x would approach negative infinity. And then for the second line, it's going to ask about the right side of the graph. So as x approaches, on the right side of the graph is just going to the right forever. So it'd be as x approaches infinity. f of x approaches, and that part's asking if it's going up or down. So the right side of the graph goes upward because the graph was increasing. So that means that f of x approaches infinity. Okay, so to determine a behavior from just the rule, you have to know whether it's increasing or decreasing. You determine that from the base and what the asymptote is. Next is, where is the graph positive or negative? And just a quick reminder, that was like saying if it's positive, that's when it's above the x-axis. If it's negative, that's when it's below the x-axis. So I would recommend kind of like saving these tables and referencing back to them. I'm going to use this little sketch kind of like as an example. So this says when the base is greater than 1, which this was for log base 5 of x. So we had a base greater than 1. That says that like on the left side of the x-intercept, which we don't really know where the x-intercept is, but on the left side of the x-intercept in this case, the function is negative between the vertical asymptote and the x-intercept. So I'm looking at this part of the table right here, and that whole thing is describing this purple section. So to the left of the x-intercept, the function is negative between the vertical asymptote and the x-intercept, and then we have the x-intercept in the middle, and then on the right side of the x-intercept, the function is positive for all the x values that are greater than the x-intercept. That's referring to that blue section. So on the right side of the x-intercept, the function is positive for all those x values, or all the x values that are greater than the x-intercept. Okay, it kind of switches when you have a like base that's between 0 and 1, like it says right here. So if I have, I'm going to draw a quick sketch of this as well so we could see it. If I have a base that's between 0 and 1, let's say I'm just going to keep the asymptote in the same spot. That would mean that the function is decreasing, so it would be going like down and to the right. So still, like, I don't really need to know exactly where my x-intercept is. This is just all in relation to the specific x-intercept of that problem. So left of the x-intercept, a function is positive between the vertical asymptote and the x-intercept. That's this section of the graph. And then on the right of the x-intercept, the function is negative for all the x values that are greater than the x-intercept. So that's saying everywhere to the right of the x-intercept, the function is negative. And that's going to be true for like every time the base is greater than 1, it'll have this same kind of like, I guess, structure of the graph. And then anytime the base is between 0 and 1, it would have that same structure as like that bottom graph. Okay, so I would definitely save these tables and use them to refer back to. Okay, so there's one more thing that we need to figure out, like how to pull from a rule before we can get into graphing it. So for the intersection of a function and y equals 1, you can also find this from like a rule itself, not just the graph. So to find the intersection, substitute y equals 1 into the function and solve for x, kind of like when we found the x-intercept. So we take y equals 1, and we replace f of x with it because f of x and y are interchangeable, so we're putting that 1 in for f of x, and then we're going to solve for x. So it would be 1 equals log base 5 of x. And then if I want to solve this, I can either exponentiate or I can rewrite it in log form. I'm going to rewrite it in log form. So the base of the exponential would become, the base of the log would become the base of the exponential. I know that logs isolate the exponent part, so the part that's by itself in log form would become the exponent from exponential form, so it'd be 5 to the first power equals what we were taking the log of, so equals x. So, and then simplify now, so 5 to the first power equals 5, and then 5 equals x. And this gives us like an extra point. It's one of the easier points to find on our function. So if we think about it, like we put in y equals 1 as like our f of x or just y, and we got out 5 for x. So that means that f of x and y equals 1 intersect at the point 5, 1. Because we got x equals 5 after putting in y equals 1. And the reason that we do that is because it kind of helps you find, that's usually one of the easiest points to find in terms of a log. Okay, so next we're going to graph f of x equals log base 5 of x, and this is the same function that we've used for like a bunch of these different examples, so we already have a bunch of key information here. So I'm going to go back to the first thing that we found. So we found, well, we didn't find the asymptote of log base 5 of x, but we learned that anything in that form has an asymptote at x equals 0. So anything that's in the form f of x equals log base b of x plus k, in this case k would be like 0, has a vertical asymptote at x equals 0. I'm going to make that a little bit bigger. So this graph or this function has a vertical asymptote at x equals 0. And then I'm going to go back up to the x-intercept that we found. So we did find the exact x-intercept of log base 5 of x. It was 1, 0. So that's going to be the first point on our graph. So we'll put a point at 1, 0 right here. And then we know we found I went too far, sorry. We found an end behavior of f of x equals log base 5 of x, that same function we're trying to graph. Our end behavior told us that it was increasing, so it should go up and to the right. So it's going to help us kind of finish our graph. I'm going to refer back to the positive or negative after. And then in this section, we found that intersection point of the function and y equals 1, which was at 5, 1. So that means that that intersection point has to be a point on the graph. So we would have a point at 5, 1. And then we can use our end behavior to like finish our graph. So the end behavior said that like as x approaches 0, f of x approaches negative infinity. So that means that as the graph goes to the left towards the asymptote, it's going to shoot downward. And then as x approaches infinity, that's the right side of the graph, f of x approaches infinity, so that side is going to finish going upward. So it'd be about like that. So we have those 2 points, and we can just use end behavior to like kind of fill in the rest of the graph. So I want to refer back up to these tables really quickly. In this case, we had a like base that was greater than 1. And if you look, like our graph matches up with what the table is saying it should be. So right here, it says the function is negative between the vertical asymptote and the x-intercept. Negative down here between the vertical asymptote and the x-intercept. And then if I look at the other side to the right of the x-intercept, it says the function is positive for all of the x values that are greater than the x-intercept. So that's describing this section of the graph. Okay, so I want to show you just kind of a quick little way that you could kind of find these 2 points without going through like, I guess, this whole process. So if our function is like f of x equals log base 5 of x, we can organize it in a table, basically the same work that we did. We can organize in a table, but work it backwards. So if this is like x and f of x, first we found like the x-intercepts, and x-intercepts occur where f of x equals 0. And then after that, we found the intersection of the function y equals 1. So y and f of x are interchangeable, so that'd be like f of x equals 1. So if it's helpful to like find it this way, which I would imagine might help like kind of streamline things, you can just create a little table like that and work it backwards. So this would be like putting 0 in for f of x equals log base 5 of x. And then if I rewrite that in exponential form, it would be 5 to the 0 equals x. And then 5 to the 0 is 1, and that equals x. So I would put a 1 right here. And then for like for f of x equals 1, I would do the same thing. I would put 1 in for f of x. So it would be 1 equals log base 5 of x, and then I could rewrite it in exponential form as well. So it'd be 5 to the 1 equals x, and then 5 to the first power is just 5 equals x, so I could put an x right here. Okay, so that could be a quicker way in the future, like to find the 2 points that you need from your graph and then just finish it with end behavior.